fields, giving us the opportunity of listening to a seminar which is aimed for no specialists. Today, our guest is Professor Roberto Cingolani, who is the director of the Italian Institute of Technology in Genova. Just to give you a few biographical points. Professor Cingolani is a physicist, and he took his degree in Bari, and then also the PhD, and he also has a PhD di perfezionamento here at the Scuola Normale Superiore. Then he has been associate professor in physics at the University of Lecce, and then full professor. And since 2015, he is the scientific director of the Italian Institute of Technology. In 2001, he founded and was the director of the National Institute for the Physics of the Matter. Professor Cingolani is author of more than 700 papers and 30 patents, mainly in the fields of structural, optical, and electronic properties of nanostructures and semiconductors, molecular nanotechnologies for plastic photonics, OLED and plastic electronics, bionanotechnologies, and biomimetic systems. He's member of various panels of the European Commission and member of different panels also of the Ministry of Research and University here in Italy. Today he will tell us about translating evolution into technology. So please.
Thank you, Chiara. So it's a big pleasure to be here again. I'm heartfelt bound to Scuola Normale because of my past activity here. I remember, I think I was one of the first experimentalists after Gozzini, building up the lab in Via della Faggiola. So this was a very pioneering time, 1986, 1987. Yeah, okay, what I want to show you today is something which has to do with the recent activity we've been developing at the IIT in Genova. Most of this activity, as you will see in a bit, cannot be done by a single man, obviously. It's a very strong system-integrated research. So at the very end, in the acknowledgement, you will see how many people will be involved. However, there are a few concepts that I'd like to share with you that belong intimately to the strategic plan of the Institute. Right now, for those who are not aware, IIT is a cluster of laboratories country-wise. Well, start with a very good technology. My laser doesn't work. Let's see this one. There's no laser working. Okay. No, this is the TV which is absorbing. Yeah. Okay, it's physics. All right, so well, there's a cluster of laboratories country-wide. There are 12 labs. The headquarters in Genova. There are a couple of more labs in the Boston area, machine learning in MIT, and the optogenetics in the Harvard Medical School. Right now, we count approximately 1,500 people. With some proudness, 41% are women. And about one half are coming from abroad. We gather scientists from more than 50 countries all over the world. And we also have a site here in Pisa, a lab in Pisa at the Nest laboratory. Okay, let me go through the idea I want to share with you. As you very well know, over the last 3 billion years, nature developed a very complex system starting from few atoms aggregated. Okay, we start with the idea of the antibody or any complex molecular system. And of course, with increasing complexity, that is number of atoms or number of molecules, the functionality of this system has been increasing in complexity too. So you go from the antibody to the virus to bacteria, and all these systems are operating through biochemical interactions. So in terms of slave machines, what is normally called a robot, these are biochemical robots. and they interact without producing mechanical work. Now, during the evolutionary process, some of these materials, some of these objects started to originate cilia, tails, legs, wings, small propulsion systems. So they started to produce work. So complexity increases because of the nervous system, of muscles, control, and of course producing energy and mechanical energy is a different story than producing biochemical interaction. So in that case, biomechanics enters into the game. So biochemical robots and biomechanical systems. With increasing complexity, of course, you go towards much more complicated systems such as insects, plants that you normally assume to be immobile objects, but they're not. Roots move essentially very fast in a very smart way. And of course, with increasing complexity, you go towards cognition. So essentially, you introduce a brain because you have to control so many functions, including social behavior, cognition, and so on and so forth. So basically, you have three domains: biomechanics, biochemistry, biomechanics, and cognition. And basically, this is what nature did in 3 billion years to reach our standing. Now, what technology is doing over the last 20 years is to reproduce this evolutionary picture into machines. And machines at the moment are, in the nanometer size, artificial antibodies. You can make micro insect, you can make robotic plants or plantoids, you can make animaloids, you can make humanoids. And of course, copying is sometimes more difficult than creating. This is an old story, as the Japanese has taught everybody. But this is actually what technology is doing now. And what I'm going to show you today is how you can go through this evolutionary pathway to show how technology and science, in turn, develops along the evolutionary description. So I will start with the biochemical robots. Please keep in mind this figure, because basically I will go from the artificial antibody down to the humanoid. So I will go step by step through the plantoid, the animaloid, the humanoid, and so on. So let me start with this description of the biochemical robots. This is a complicated puzzle machine. It's very small, below 100 nanometers. Otherwise, the immunitary system would detect and stop it. It's a very complicated machine in terms of robotics, if you wish, as this includes imaging capability, sensing, drug release, and responsivity. This is a system that travels into the bloodstream. It's capable to sense the disease, that is to identify the cell or the molecule, whatever, which has to be tackled, to release an image, so we have to see where is this cell, to release a drug, and eventually to release the drug according to a specific response to pH variation, to temperature variation, whatsoever. So it has to be a responsive, intelligent machine, capable to release a payload, a drug or whatever, giving an information where this is released, and of course, sensing this at very early stage. Now, there are hundreds of solutions being under investigation at the moment, liposomes, all kind of polymer constructs, and so on and so forth. What we decided to pursue as a strategy is a very unique strategy, relies on super paramagnetic nanoparticles, which are clusters of approximately 20,000 atoms, diameter in the range of 10 nanometers, tetrahedrally coordinated. These super paramagnetic particles essentially expose a lot of oxygen surfaces, which can be easily functionalized in a way that you can grasp responsive polymers around. The responsive polymers is capable to uptake and release, according to specific stimuli, any kind of drug, even multi-drug combinatory therapies, so anti-inflammatories plus chemotherapies and so on. And at the outer shell, at the outer surface, you can grasp covalently molecules which are capable to recognize the receptor of the disease and eventually fluorophores and everything needed for imaging and detection. As a matter of fact, this kind of cluster is approximately 120 nanometers in diameter overall, and it can load up to 95% in weight drugs. So normally they have a magnetic responsivity which is superior to the endorem. The endorem is the typical NMR contrast medium that you find on the market. These are the best performances in the transversal magnetic resistance. They are quite interesting. You see, this is in a UV lamp. The particles are in water solution because these are water soluble. They move, they fluoresce, of course. They move around the magnet, so they show very convincing collective motion. That means that one by one, they can be conducted either by an external magnetic field or biochemically, and they don't cluster because they have a very specific surface functionalization. This is typically what we mean with this technology. In the presence of an external oscillating field, so radio frequency, the temperature of the superparamagnetic particles can be increased up to some 50 centigrades. And if you develop by colloidal nanochemistry, colloidal deposition, you can develop particles of very controlled shape. This bar is 20 nanometers. And of course, depending on the number of edges, you have a very high concentration of electrostatic field in an electrodynamic concentration of field so that you can increase the temperature in a very effective way. And in this case, you can apply not only smart delivery of the drug, but you can also increase the temperature for hyperthermia, which is an extra characteristic of this smart robotic antibody. Of course, you can play a lot with the shape and with the characteristics. I mean, this is just a compilation of shapes. You can make cargo nanoparticles clustered in a polymer shell. You can make quantum cubes. You can make complex nanostructures, each one having specific features in terms of release, transport, and so on. So really, you can do a lot by colloidal chemistry. This is now to show you how it works. This poor animal has been treated in a specially designed hyperthermia system. Actually, in this case, we work with 30 millitesla frequencies, which are quite standard. And this specific mouse has been treated with nanocubes, so this quantum cubes I've shown before, by using doxorubicin. Just to give you an idea what happens in terms of imaging, this is the intratumoral heating, where you can detect by special camera the temperature. After 30 minutes, the hyperthermia is quite effective. You see at the core, you reach something like 40 to 41 centigrades, which is almost enough to kill thermally the cells. But what is more important is that the combination of the chemistry and the hyperthermia provides very interesting results. I mean, this would be the control. This is the normalized tumor volume. This is the control animal. This is only the hyperthermia 10 days after injection. This is the chemotherapeutics as standard, and this is the combination of chemotherapics and hyperthermia. So it's really a powerful tool, and the idea is that you have one cell, one nanoparticle. So this is meant to be a very selective scalpel somehow. It's a surgical intervention in terms of therapy, because you can really control the dose without counterindication in terms of massive chemotherapical doses that you normally apply to patients. Okay, I don't have the time to go through all these things. I'll try to give you a compilation, but of course we can discuss in more details later. I want to swap directly from the very small things to the very big things. This is the plantoid. This is something, by the way, developed partly also in Pisa, because the PI of this new robot generation is Barbara Mazzolai, who's a scientist originally started her career in Pisa, and then now she moved in Genova. Now let me show you what is the concept here. This is actually the first plantoid robot in the world. The leaves are responsive to humidity, and they are photovoltaic, so they generate energy for the intelligence of the robot. This is a root, actually. The root exhibits the basic properties of roots in nature. So gravitropism means that whatever is the inclination of the plant, the roots always points towards the center of mass of the earth. This is why plants are stable, independent of whether they are on a hill or on a flat ground. So they always keep the gravity at the center. They are thigmotropic, which basically means that they avoid obstacles. So roots don't like to grow where there is an obstacle, and they find another way. That's why plants, they always survive. They are hydrotropic, so they go towards the water, because this is the basic food. And they are thermotropic, so they don't like heat sources. So if there is too much high temperature, they just escape. Now, giving this properties to an infinite elongating screw, flexible, by a technology that I have no time to tell you, the idea we're trying to develop is the smart endoscope, which you see here. So essentially, it's a technology that at the tip of the root has the same intelligent nanoparticles for the drug delivery that finds automatically the disease and goes there by growing into the body without surgery. So this is called, or supposed to be, the smart endoscope. So this is the long-term target of this research. In the meantime, another smart application that I'm going to show you here, this is a cartoon. It is that for aerospace application, when a satellite lands on an unknown surface, and this happened on the comet recently, on the Rosetta comet, the rover fell, if you remember. This system, these small satellites can elongate their routes, stabilize, get energy from light, and incidentally making the ground analysis, because these routes have the intelligence and the sensing system to make the ground analysis. So for aerospace, as well as for agronomy, this is a very smart technology. This is why it's being developed now, but of course the long term is for the smart endoscope. This is how you can copy nature to do something really useful. Now I go to the animaloids. So I'm moving towards the complexity pathway towards something very big, 10 to the 27 atoms, so much bigger. And I want to show you, obviously, the first thing that people want to copy is animals. This seems to be a very massive machine, but it can do something that only goats can do. Okay, this is our hydraulic quadruped. It is actually the most versatile quadruped in the world at the moment. It was probably 2 years ago. Now it is. It has an intelligence essentially given by the combination of vision and a vestibular system like ours. So horizon, center of mass stabilization, capability of dynamical equilibrium, so that it can change the pathway in any circumstance. So for instance, here we change the landscape, and it reaccommodates immediately the walk. Now, this kind of machine has been developed for a number of applications. Definitely disaster recovery. I mean, we live in Genova. We have a flow every couple of years with many people dying. So the first order we got was from Protezione Civile. Because this is really a machine that can go everywhere, where no whales, no humans can go. Imagine Fukushima. The problem in Fukushima was a trivial problem. People could not enter into the nuclear power station because of the radiation field, the average radiation density. This machine could have been inside very easily. Look at this. This is like a real animal. 30 kilos bumping laterally, and it takes just 3 lateral steps to recover the equilibrium. So I go back to Fukushima. The point was how to enter in Fukushima. That was a biped under the same experience. So you enter in Fukushima, and then at this point you just need hands to rotate a valve. Now, the trivial thing is that on this quadruped, you can easily install an upper body with arms and head and whatever. So you make a Centaurus. I'll show you something later. So it's very easy for a machine like this to enter in Fukushima and then to operate under remote control eventually, even without important intelligence, to change the status of the pumps, to rotate the pumps, and so on. Okay, I want to show you something now that is, to my opinion, biomechanically extremely relevant. This is the last version, the most advanced quadruped you can find at the moment around the world. This is a Jaguar. It's an extremely fast machine. Now it is upside down. It just fell. Okay, imagine the animal was falling, and now look how it will recover the original position. This is exactly what you call colpo di reni, kidney shot. And now it's ready to move, run, rush, attack, whatever. Okay, clearly this machine has not been designed for military application. This is a machine that can bring 75 kilos on the shoulders, is as big as a big dog, and it's meant to run 25 kilometers per hour on any ground, under any condition, completely self-powered. At the moment you see some pipes because this was a lab exercise. But now it is completely autonomous. So you just push a button and it goes. And these are, even for mobility, very, very interesting new devices. I mean, one day we could go back to horses, like the cowboys, but riding a horse which is fully mechanical, and having a consumption, energy consumption, which is about 1/3 that of a motorbike, because of the advanced, very, very advanced biomechanics. I mean, that's a scenario we don't care so much, but just to give you a fantasy idea. Now let me go to something more serious. This is my 3rd kid. I have 3 children. This is my smallest kid. He's 6 years old. His name is Alkis. And this is, well, I cannot say my 4th kid because it has approximately 400 parents in the lab. It's a very complicated machine. But this, I think you have seen this even in the telecom advertisement recently. It's a little star. Actually, this is the most diffused humanoid platform in the world. There are 34 robots at the moment. And it overcame the Asimo from Honda. It overcame the Toshiba robots. So he really seems to be an exceptional breakthrough of the Italian community. But I want to tell you where we are now and where we go. So Alkis, my son, never stops with 1,500 kilocalories per day. Essentially breaks everything around without stopping, 24/24. And he has a very low energy consumption. He holds 10 to the 14 synapses. That's a mistake, not neurons, synapses. He holds a 3D structure for the brain, 75% water, approximately 10,000 interconnections among neurons, for a total power of 40 watts. This is the brain consumption. It can perform, like any other human, normal human, 10 to the 18 operations per second. I doubt everybody can do this in some area, but for sure in this room everybody does at least 10 to the 18. Okay, on the other side, sorry, we have 10 to the 9 transistors. We have a 2D structure, silicon, like this. Each transistor is interconnected to only the nearest neighbor's 10 transistors. And you know by the Ohm law that the far away you go, the higher is the energy consumption. This does not happen in the brain. And that's why we pay approximately 200 watts to perform only 10 to the 8 operations per second, which is the cost of this computer. All the rest has to be done in a big server with a big supercomputer in remote operation and so on and so forth. As a matter of fact, iCab needs 1,300 watts for 2 hours operation, in which it does very little compared to my kid that can do by far more with only 1,500 kilocalories. And if you compare kilocalories and watt, you will find this ridiculous amount of power that the human needs to do much more than any robot. Even the best robot in the world does not compare. So that is the challenge. And I will show you where we go with this. So first of all, artificial intelligence matters here. Neurons versus transistors, electrons versus ions, adaption versus interconnections. These are the 3 things that possibly are unbreakable barriers. Then there are a number of other technologies like learning adaptation, speech and audition, grasping and manipulation, biomechanics. I mean, the robot has screws, motors, cables, coils. We have fibers, ion responsive systems, water conductivity versus copper. You know, it's a very different architecture. Actuation is completely different. So what happens today, if you take this very famous Kurzweil plot, this is a little bit science fiction, but I think Kurzweil now works in Google, so he's not the last guy in the world. And he said, if you see how computer grew up over the years, a good computer today performs 10 to the 8 operations per second. And if you want to do more, you need a big cluster, you know. So today you can do exaflop computing, but you need 35 megawatts of power. I think, Vincenzo, you know it because you built up a new computer center, and I'm sure you need kilowatts and kilowatts for that. Now, surprisingly, humans, they do 10 to the 18 operations per second at a very low computational cost. We can do the same synthetically, but we need 35 megawatts. So this is a big problem. And this is a supercomputing, this is a top 100 supercomputer map. And you see now we have this Cray XT5, and there is this super Whooper computer in China, exaflop machines, but they just need 30, 35 megawatts of power. So again, this has to do with what I told you before. If you compare the brain of my kids and the brain of the robot, those numbers essentially are the basis of this difference. But there is also something much more advanced that we should never forget. This goalkeeper doesn't know anything about physics. He doesn't calculate air friction. He doesn't calculate aerodynamics. He doesn't know anything about initial speed, gravity attraction, spin. He doesn't know anything. He just sees the ball, jumps, and he will touch the ball with the hand at the right place at the right moment. He doesn't know why, but he does it. If you want to do the same with a supercomputer, because you need a supercomputer, you have to do a variational calculation of the best trajectory, minimize time, space, considering all the boundary conditions, and setting the best trajectory to be at the right time with the right hand in the right position. Unfortunately, in doing this calculation, very likely the calculation will last more than the shot. So by the time the calculation is finished, the ball is in the net. So that's the point. And the reason is that in our brain, we are so much optimized by evolution that there are clusters of neurons that supervise completely different operations that are very synergistic. For instance, there is a class of neurons that are essentially controlling vision and controlling grasping. So the same part of the brain helps us in understanding what we see and help us in reaching, so controlling the movement. Another part is controlling the tongue, so the operation of the mouth, the speech, and the understanding of the words. So this kind of synergy is impossible to reproduce in a computer at the moment, primarily because of an interconnection problem, primarily because of a computation problem. And this is really, for the time being, an unreachable challenge in terms of technology. Neuroscientists, they know these things very well. They start having a fantastic description of the brain. And technologists, physicists, engineers like me and others, we are very frustrating. The more they understand, the more we see that we cannot reach, we cannot compete with the structure of the brain. So right now, I can tell you that if you take a computer and a mechanical actuator, I don't make a humanoid, I don't make a robot, I just make an industrial actuator. And if I make a humanoid, I'm still far from a human. I mean, this equation will last for at least another 20 years. It has to be very clear. Now, in the end, we will discuss about ethics. You could tell me, okay, what is the point to make a robot? You can make kids. It's easier, it's cheap, it's even more pleasant. So why you need an artificial body? But that's a good question. But it has a real rationality, this kind of science and research. The point is that we want to have machines capable to decide, capable to act in response to specific situations. We don't want emotional machines. This would be a nonsense. There is no hormones in these machines. But we want smart machines to replace people in dangerous environment, to replace people in harsh environment, to help people at the workplace, in the house, when they're old, especially in a society that in the next 30 years will have one active person per retired person. I hope this is clear to everybody. In the G20, in the next 20 years, we will go to one-to-one ratio among old people and working people. And that's the issue, because who's going to take care? What the welfare will do. So who is afraid of the fact that we're going to lose jobs? It does not consider that jobs will diminish because workers will be less and less. So that's a completely different vision, but I will comment this at the very end. So clearly, there's no way to give an intelligence to a machine with a resident computer because the computer is too weak, is too little performing. So for the future, let's say next 10 years, for sure, there will be a machine like a super mobile phone capable to actuate movement, connected to a very fast wireless protocol like 5G, 6G. We need to go into the 300 megabyte per second, otherwise it's too slow. When you say to the robot, give me that bottle, you should not take 2 seconds to understand the indication. Pointing an object and recognizing the object for a robot is a very difficult thing. And this should take less than 0.1 seconds in humans. It should take the same in humanoids. And then, of course, you need a cloud. That will be the global repository of all the experience and the intelligence of all these machines, so that you buy your robot, like you buy your telephone, you bring the robot in the house, the robot will explore the house, will see all the constants, limits, landscape, and then you will say, okay, bring me the newspaper, or cook 1 egg. And the robot will have approximately 0.3 seconds to connect to the cloud, get the recipe to cook the egg, and make it. Okay, you're laughing now. But if 20 years ago, somebody would have told you, in 15 years, you will see your email, your TV, your Twitter, Facebook on your phone, you would have been laughing. You would have been laughing for sure. So that's the same story. You will see. Now, it's not by chance that Google purchased all the robotics in the world. It's not by chance that now the giants of the ICT are fighting for the control of the cloud. I mean, this is something really beyond our heads at the moment. So let me show you now how this is being implemented. In order biomechanics to be effective, you need senses to be synergistic. We are machines integrating tactile inputs, visual inputs, and acoustic inputs, at least. And from this, we have a perception reality, and we act consequently. So at least we need to reproduce the senses of the human body, to integrate this in a machine, and to give a code for the use of these inputs in a way that then you can decide the machine can decide what to do next. So the first thing is the skin. Tactile capability is one of the most important things for a social machine. This machine now is completely covered by tactile skin, and this is a vectorial machine. So not only can feel the touch, but can also understand whether you're pushing or pulling, and after this decides whether it wants to hold you or keep far from you. First social impact is tactile impact. And once you have a tactile capability, you're no longer an XYZ machine. So I don't give you the coordinates, I just show you the trajectory. And if you work with trajectory, you become a dynamical machine. You're no longer a cinematic machine. This is exactly the example I'm telling you. Once I show you how to fill the cap with the cereals, you don't learn this movement because, like in the automatic, in the automation in the industry, this cap is in XYZ position. You just learn a trajectory. And if I move the target, you change the trajectory because you have learned the dynamic of the process. You didn't learn the final and initial position. This is why we said that if a robot is force-controlled and torque-controlled, it's a safe machine. What happens in the industry? You have a big cage. There's a robot doing this trillions times a day. And if by chance a human passes through, it will kill the human. This happened very recently. This is position-controlled, XYZ. This machine would never kill a human because it's like us. If I do like this, I feel, oops, there's an object here. So I feel something. I understand that by vector, I cannot go further. I have to go back. And so I'm a safe human. And the machine, to be safe, needs exactly the same capability. And then you need the intelligence to, of course, to interpret this sensorial input consequently. The robotic skin is a capacitive machine. Okay, I'm a physicist. I have to go back to some physics sometimes. This is a capacitive sensor. It's a soft electronics, completely soft, can bound and wrap completely all parts of the body. It is temperature drift corrected. Well, for physicists, this is a tricky thing because capacity changes a little bit by temperature, and this is corrected. It's a very sophisticated electronics. It has a resolution of few microns in position, like the human skin. And there is an intelligence that correlates the vestibular system, which is 3D acceleration, 3D rate of turn, with very high angular resolution. So this is the vestibular system we have in the ears, basically, this equivalent, the input from the ears. And then we have special motors that incorporate torque control, force control, position control. So the feedback given by the tactile capability controls directly the motors, so the actuators, like the muscles. And these are interconnected with the vestibular system to keep the equilibrium and the position. It means, to give you an idea, approximately 2,000 sensors integrated in a unified control system. The intelligence in this case is biomechanical intelligence, means taking measurements from the inertial, like gravity parameters, position, velocity, acceleration, force, torques, compute the external forces by combining location from skin and intensity from the force torque sensors, removing any internal dynamics, including inertial Coriolis and gravitational effect. Otherwise, you cannot go exactly where you want. And then compute movement depending on the external forces. This thing is done in a fraction of a second. And this starts to be a very big challenge in terms of control, electronic integration, nanotechnology materials, brain imitation. Okay, that's a paradigmatic idea. The gaze stabilization, for instance, is something typical of humans. You can never do any exercise like this if you point towards the ground. You really need to see the horizon, otherwise you cannot keep your equilibrium. So the robot really behaves like a human here. Even better, this could be a professional dancer or a martial art expert. And you see, how impressive is the dynamical equilibrium here? Because the robot reacts real time to external perturbation. Try to do this with a human or with any other machine that you are aware of. Okay, of course, we can learn more lessons from nature. You know, I've ever seen swarm motion, like these little fishes in the water. The first fish moves and all the others, they go fastly and simultaneously together. I mean, how do they do this? Or the same is for birds in a storm. Actually, fishes have hair cells, very sensitive cells that upon vibration due to viscoelastic perturbation or turbulence, they produce electric signals. So these are like piezoelectric materials. Now, we're reproducing piezoelectric plastics by using special polymers. We create devices. These are kind of soft nanotechnologies. Devices are like cilia. This is approximately 400 microns by 100. with a totally flexible technology, including the conductive part. And upon vibration, these things produce energy, they produce current. And this current can be used either to power a system or to sense a change of turbulence, so to direct the movement, so to make skin, basically, new skin. This gives you an idea how sensitive this thing can be. This boy is blowing 1.2 meters per second, like this. You see this little plastic foil, and you see here the current generated is approximately 10 milliwatts. It's a huge amount of power, just transforming air turbulence into electric power. Of course, you have two possibilities for that. You can make the most sensitive skin ever seen, artificial skin ever seen in the planet, very expensive, or you can cover your jacket with this thing, or underneath a boat, and exploiting the turbulence of the viscoelastic medium around to generate current, to power your GPS, to power your telephone while you pedal the bicycle and so on. So this is how, without even having a plan for that, you produce a technology that goes directly into energy production. This is called energy harvesting. It's quite a field now. It's growing a lot, and there is a very big potential market. We did this for, actually for the skin, but it came out to be very sensitive. Another thing I want to tell you, the forecast is that in approximately 15 years, there will be 1 billion robots on the planet surface. Approximately like the cars now. And you know, one problem with cars is that they're not biodegradable. So people are trying to recycle plastic, they do their best, but as a matter of fact, polymer plastic degrades in approximately 1,000 years. And this is actually a consequence of the polymeric structure. Now we can use other polymers, sugars like cellulose, that can be recovered by natural sources. Now for your information, Italy produces 26 million tons of vegetable waste every year by the food industry. And this is just waste. There are reactions that can be exploited a little bit similar to what is being exploited for bioethanol, but not exactly the same, in a way that you can recover natural cellulose from the vegetable waste. And then you can reassemble in a way that, for instance, this is parsley plastic. The parsley is produced in Alessandria. You can do with potato. You can do with with tomato. You can use any we are working with all the most important food companies around the country, and you can make plastics. Actually, the interesting thing is that if you compare in this, if you compare in this plot what you can do with this plastic, if you compare the ultimate tensile strength, the breaking charge, towards the young modulus, that is the flexibility basically, you see that you go from PDMS, which is the rubber of the kitchen globe, it's very, very soft, very elastic, up to the PET, which is the plastic of the bottles, very tough. Well, you can cover the entire mechanical range by using spinach, parsley, rice, cacao, and different combinations. So just by recovering cellulose from the waste of the food companies, you get plastics whose biodegradation time does not exceed 24 months. They are attacked by bacteria, so they can just dissolve in nature. But in terms of mechanical properties in protected environment like here, they can last for years. So this is now being implemented into the external scaffold of the robots, because the first thing we have to do is we have to make a robot which is sustainable. Don't think now. Think in 20 years when this will be a problem. The average lifetime of these telephones is a couple of years, and now you read on the newspaper that there is a problem about all the electronic waste. We don't know how to manage. It's full of toxic materials and so on and so forth. Another important issue, we want to go towards the biomimetic thing. So we need to have very flexible systems. We don't want to have cables, wires, copper, these things. We need plastic in the mechanical sense, flexible circuitry. Okay, here in Pisa, we launched, together with other guys in Genova, a huge initiative about graphene. So graphene seems to be a very magic material. It cures the common cold too, but it's not true. I think that the real good point of graphene is that it's a jewelry material. It's too expensive. It's too difficult to handle. I don't think it will have a great future in itself. The real future of graphene is that you can make very small pieces, each piece being almost monoatomically thin, very, very ordered hexagonal carbon structure. It's soluble and processed in a way that by ultracentrifugation and ultrasonication you can make an ink. This ink can be inkjet printed. And at this point, you do very simple things that are very biomimetic. This is a piece of paper, just a piece of paper, the angle chip. There are two stripes of this ink, like to brush things. This is an LED. This is connected to the USB port of the computer. So a piece of paper is a very flexible conductor you can use to make a circuit. We say, okay, fine, but we already know other plastic circuits. But you cannot treat a plastic circuit like this. Because this, to my opinion, is the real key point of a hybrid composite that is based on graphene inks and graphene nanocomposites. So this is 100% biocompatible, almost unbreakable. I think you would never dare to do anything like this on a circuit, I'm sure. This is a piece of paper. Now imagine that you can print, you can design all your circuitry in the robot directly into the elastic scaffold. No wires, no connection. You just print all the circuitry. You see it still work. By the way, you can get electric conductivities at percentage of these composites in the range of few percent in weight that are very, very, very close to the metallic conductivity. You see here how the sheet resistance drops. And in the meantime, you have an increase in the Young modulus that gives you an idea that meanwhile you make the material conductive, you make the material more robust, which seems to be a very interesting property because we are talking about a biodegradable and extremely handleable material. So I'm going towards the end. 5 minutes, 7 minutes. What next? There's an artificial intelligence shopping list. We want these machines to learn by action, to be adaptive, to imitate. Because at this point, we need to coordinate vision, sensory motor coordination, and speech in a way that the robot, the humanoid, becomes really social. So can interact with you. There are many things that I'm not going to show. Learning by action is one of the issues. This implies a lot of big data analysis, machine learning. It's not easy for a machine to select in the landscape of millions information which are those relevant to the next action. So here we merge machine learning, big data, and of course neuroscience in a way that should be developed synergistically. We are at the very beginning in this field, but actually, I mean, in this movie, there is a simultaneous representation of 3 learning by action examples in which the robot has to essentially approach an object which is out of reach by using a tool. Essentially, the object is too far, and you want to approach this object, making the object closer by using the tool. And there are different strategies that combine, of course, vision, tactile capabilities, and so on. And in the end, one is good, the other are not. So the robot learns by action. And of course, this lesson should be stored in a global repository of intelligence. Will never be resident forever, like in our brain. So this is a limitation. But anyway, the robot trains in many circumstances. Here, for instance, there is a convolutional neural network approach for recognizing objects. The robot is constantly trained for recognizing real objects. So this is a very interesting experiment. This again, once again, is vision and machine learning together. So you see, imagine you have 25 objects to recognize, all these things, the brush, the bottle, the plate, and so on, common objects. The larger the number of objects, the more the robot should keep the attention to recognize them. Of course, you want a fast machine like us. When we see an object, we take a fraction of a second and we know what is this. The robot, for only 25 objects, needs, in blue, essentially, let's see, in red, 5 seconds for 25 objects to have a mistake rate of approximately 10%. So imagine, we recognize millions of objects simultaneously. The robot, for 25 objects, with a repertoire of 25 objects, requires at least attention for 5 seconds to make sure having a good recognition. So this prevents the robot right now to be in real environment. So this requires a very advanced simulation of the process of vision and recognition. So this is a lot of mathematics. There's a lot of, again, machine learning. And then this has to be transferred into control codes. This is the typical situation in which you teach the robot to recognize many objects. This is how the robot has learned to write. ICAP can write now. He has learned the alphabet. He has learned writing. Now, when you test the system, essentially you put all the objects on the table and you say, can you recognize the octopus? Can you recognize the fish? And then the robot needs a few seconds to find the right object, which is already an outstanding result, because this is a real confrontation. It's a real world. It's not a simulation, actually. Obviously, there is a 3D awareness, because it's not only to see the object and recognize, but also to have a telemetric vision of the object. So the robot has to have a real and a virtual reality description of what it's observing. And this is very important, because then grasping is connected to the representation of the 3D reality. So when we see an object, we have a 3D representation, and roughly we know that by elongating the hand, we can touch it or grasp it. So for the robot, it's exactly the same. Sometimes the robot is completely uncalibrated, so it needs a sort of telemetric calibration of reality like this. It has to span all the horizon like this to have a telemetric representation. These things actually are not simple programs that you do with the joystick of the PlayStation. You operate by remote. This is just the intelligence of the machine. They require a tremendous effort in terms of development. And the first thing is to have neuromorphic cameras. There's a lot of technology here. So neuromorphic cameras are cameras having at the center, typically, let's say somewhere here, just a small bunch of pixels. We're talking about not more than 10,000 pixels, okay? Normally cameras are megapixel, millions of pixels. But you need a neuromorphic camera. At the center, you want something which is dynamic, is differential. So we don't care about observing reality and accumulating images. At this moment, I'm watching you, okay? 95% of what I see is not changing in time. So I see it once and I keep it in my memory. And I only see what is changing. For me, it's obviously automatic. For the machine, it's impossible with nowadays technology, unless you have a neuromorphic camera in which the central part of the camera only perceives time variation in the image. And the rest is just a stable part. So you save memory. This essentially allows the machine, allows the robot, to see dynamically things. This is a real image. So it's a cube, rubric cube, yeah, changing. And this allows the machine to have the gaze in real time, almost real time, like humans. Essentially, you see, it's almost synchronized, not as fast as we would like, but the gaze is synchronized to the real motion of the objects. No machine can do this with normal cameras. And this is very important because then the robot needs to interact with humans. This is the Simon game. Actually, this got the Microsoft Kinect award, second, recently in Providence. So the robot is playing with one of the trainers. This is one of the robot trainers. She's a girl spending a postdoc in our place. So they are playing. Essentially, this is the Simon game where you do a movement. The other has to copy and has to add another one. And then you have to reproduce a sequence till you make a mistake. Of course, the robot always wins. Normally, he wins at the 8th or 9th movement. It's very long. But it's fantastic because he can really now recognize real-time the movement, reproduce it, and generate a new one. And in the end, the girl will fail. The robot will never fail in this. So,
yes, hello.
Ultimately,
Hi, hello. Nice to see you. Hello, Aika. Here. Hello. It's nice that he actually is sort of like a little child. Call him pretty loudly.
okay, what I'm showing you here is one of the first experiments of social behavior. I mean, now the machine is doing everything it can do autonomously. Two guys are talking, calling the attention. The machine is, okay, it's a bit slow, like a small kid, and it's trying to adapt. So there is a focus in the attention. There is, of course, a synchronization of speech recognition, social behavior, basically, vision and sound together. And the silency map is designed in real time, so the robot tries to follow all the inputs coming from the surrounding reality. Well, I conclude just showing you something that, to my opinion, is, it goes back to real life. What I've shown you before will possibly be something useful in the future and possibly be something in all our houses in, let's say, 10 years, at the cost of a scooter. On March, we will deliver the first plastic robot. This will be a machine for approximately 12,000 euro, market price. It will be capable to operate in the house and to assist people. This will be the first robot like this, that tall. So we're really moving towards something for the house, not only for science fiction. But there's something more important. Now, how can we use these things? So I want to show you one of the first deliverables, which is to help people having serious problems. This is a very unique hand. It's 100% plastic, additive manufacturing, so 3D printing. And as you can see, there's only one motor. This one motor reproduces 85% of the human movements in terms of grasping and hand manipulation. So it is now being tested on approximately 100 patients in several hospitals, from the Mayo Clinics in the United States to the Budrio Center in Inail, in Budrio. These are some of our patients. So what we do, we realize the passive prosthesis. The passive prosthesis is very standard, okay, what everybody has. But in the passive prosthesis, there are myoelectric contacts that are being developed by our people, and they register the surface electric fields due to essentially the muscle and tendon tension. And this is one of the users, after 3 weeks of training with this hand. Actually, all the electronics is here. You see, this guy was amputated 35 years ago. At the age of 15, he was an handcraft. He has tried all the prosthetic system on the market. Normally, these prosthetic systems are very complex, costing in the range of 50,000 euro, and essentially very difficult to operate. Actually, this one is essentially like a glove. You can remove this anytime. You have only a Velcro strap here for the electronics. The cost of a prosthetic system like this is in the range of 7,000 euro. So it's a total drop compared to the market. And now this will be, as you can see here, will be used for very intensive use, like starting again to work in the lab. This is possibly unbelievable when you see it. It's really... So now there's a second prototype of the hand, which has also the bent finger, in a way that you can take the credit card or the bancomat, which is what all the amputees required. So not only to have the grasping like this, but also having this movement, which is functional to take a credit card or to insert things in a very thin place. So this is going to be the next release, and by next year this will be on the market. Okay, so empathy, I'm not going to say anything. Clearly, empathy is something unidirectional. When we see TV, TV does not see us. The same will be with robots. So very likely, the design of this robot played a very important role in becoming the most diffused robot in the world, because it's handsome, it's beautiful, it's cute, but it's a machine. And these are my thanks to all the people in the ICAP team, in the smart materials, in the graphene team, in the retina team that I didn't show, in the MEMS team, and so on. So this is obviously an ensemble of many people working. Every PI here has a big group behind, so it's more than 400 people working on those platforms. And you're welcome if you want to visit the lab to see these things in real environment, real time. Thank you.
So, thank you very much. It's been amazing, and I think that there will be many comments, questions.
I'm not going to ask you something about plastic because it's too long discussion.
Yeah, I'm sure.
It's not detailed. Just two minor questions. One purely technical, and it was not clear to me what kind of material you propose for obtaining a conductivity similar to metal. It is a homogeneous distributed conducting, like nanocomposite, or you have a heterogeneous distribution?
That's a polymeric matrix which embeds some 1% to 5% in weight nanoflakes of graphene, and the mechanism of conductivity is hopping among the islands. So there's a critical interflake distance for which you optimize the conductivity, but also roughly at the same range you optimize the mechanical properties, which is a property of the matrix, by the way. So if you operate properly in the matrix choice and in the flake dimension.
Matrix was completely isolating?
The matrix is not conductive. It's a hopping mechanism.
So that's much higher than the normal values.
Sure, of course. Yeah. It's unbelievably high. Yes. By the way, this is like PLE, or it could be matter B polymers,
Okay,
or it could be things that you can hot press.
Plating product.
Absolutely, yes.
Second question is completely out of my knowledge. In the past, I had the opportunity to participate in a European project on artificial brains. There was a guided, coordinated by Professor Marco Fontana.
Oh yeah, I remember Marco. Yes.
Good opportunity to remember him.
Yeah.
And at that time, we were working about the learning by favoring a signal passing always in the same direction. So in that sense, I was wondering, if you, when you repeat an experiment with one robot, repetition makes some changes, or is the robot learning something by repeating the same thing?
In most cases, our artificial intelligence procedures are kind of trial and error procedures, so that you, of course, you increase precision or accuracy, but the relative accuracy from measure to measure decreases, so it saturates towards the best movement. However, when you switch off the robot, you forget everything. That's why you need the cloud.
Has no memory.
Exactly. If you want to have an always-on robot that is a standby machine, you can do this, but you easily saturate the memory, because the memory is one of the most expensive in terms of power, the most expensive system. So you forget having a big memory, 24/24 operating in a machine. That will cost in energy much more than all the rest. So you better have a cloud with big problems in privacy, and of course we are aware.
We have to take care of our memory.
Absolutely. Parkinson is something that will touch also machines.
Yeah.
Other?
What about miniaturization of robots in the IIT?
Yeah, I think that when they are very small, I like to call them biochemical robots, as I said in the beginning. So I think they have to be in the macromolecule size, or let's say 100 nanometers, more than a macromolecule, but they cannot be bigger than that. Otherwise, they become just intruders into the body, and they are attacked by the immunitary system and so on and so forth. As long as you go on a bigger systems, they become anyway micromechanical systems. So biomechanics play a role, definitely. I mean, I think that the real boundary is when biomechanics starts playing a role. Below a certain dimension, it's only microfluidics, fluidodynamics, biochemical interactions, and there you play with different rules. If you have anything biomechanical, then you need a power source. If you need a power source, I cannot say this in an elegant way, but of course, let's say you're in trouble, okay? Because you need something heavy, something rechargeable, toxic, and that's another story.
Very simple question. How powerful is the artificial hand that you were showing at the last slide?
Oh, yes, thank you. I mean, I have to say, I was asked to give some kind of dissemination-like information, so I was not very precise in certain respects, including plastics and polymers. So it was somewhat more shallow, the presentation. So, numbers about the hand. This prototype that you have seen is a machine, is a hand with 9 watts of power, which is enough to grasp one liter bottle. This was developed together with our friends in Centro Piaggio in Pisa. This is the first prototype. Now the new prototype, which is more advanced, having this toe that I told you before, it can run 30,000 cycles, which means years, no? With the grasping power up to 3 kilos. That starts to be quite a good thing, like shaking the hand to somebody. If you do it 3 kilos, the guy will say, hey, what are you doing? Okay, so it's a serious grasp.
Any other?
Well, on the other hand, you saw the guy with the drill. So for this, you need approximately 1.5 kilo. Of course, the other hand was pushing, but with the prosthetic, you were keeping and running the switch. So it was quite okay.
Are there any Okay, if not...
Thank you very much.
thanks again.